This edition of Space Time is brought to you by Audible.com. Get a free audiobook download and a 30-day free trial at www.audibletrial.com/spacetime. Over 180,000 titles to choose from for your iPhone, Android, Kindle, or your MP3 player. That's audibletrial.com/spacetime for your free audiobook. This is Spacetime Series 20, Episode 4, for broadcast on the 13th of January, 2017. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. You can download Spacetime as a free twice-weekly podcast just about everywhere, including iTunes, Stitcher, Pocket Casts, Bytes.com, YouTube, SoundCloud, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C. Coming up on Spacetime, a stellar collision predicted for 2022. The deepest X-ray image of the universe ever taken, revealing new secrets about black holes. And our own galaxy's black hole, flinging Jupiter-sized projectiles into space. All that and more coming up on Spacetime.
Welcome to Spacetime with Stuart Gary.
A pair of stars expected to collide in around 5 years should cause a blast powerful enough to be seen from Earth with the unaided eye. The latest observations reported to the American Astronomical Society conference in Texas claims the stars, which form a contact binary system known as KIC 98322227, have already merged their atmospheres and taken on a distinct double peanut-like shape. The stars, which also form an eclipsing binary with one star passing in front of the other as seen from Earth, are now orbiting each other every 11 hours. The system's located some 1800 light-years away in the constellation Cygnus the Swan. Astronomers predict that when they finally collide, around 2022 sometime, the explosion, known as a red nova, will increase in brightness some 10,000-fold, becoming one of the brightest objects in the night sky, certainly bright enough to be seen without a telescope. It's the first time astronomers have predicted a red nova event with such certainty. The study's authors have been monitoring KIC 98322227 since 2013, detecting a steady slowdown in its orbital period. The rate of this slowdown is expected to accelerate as the stars come closer to collision. Similar observations were seen shortly before another stellar merging event in V1309 Scorpii back in 2008. If the team led by Larry Molnar from Calvin College are correct and the stars do merge, it will open a new chapter in science's understanding of stellar evolution. Previously, astronomers had only ever seen the aftermath of these stellar collisions, not the machinations of what's actually happening in the lead-up to such an event. Molnar and colleagues intend to continue studying KIC 98322227 in all wavelengths over the next few years, using the Calvin College Observatory and the Very Large Array Radio Telescope, both in New Mexico, as well as NASA's Infrared Telescope facility in Hawaii and the European Space Agency's Earth-orbiting XMM Newton X-ray Telescope. Studying the system both prior to and during the collision will tell scientists about the physics taking place during these colossal events. You're listening to Spacetime. I'm Stuart Gary. An unparalleled image from NASA's Chandra X-ray Observatory is giving astronomers their best look yet at the growth of black holes over billions of years, beginning shortly after the Big Bang. The observations, reported in both the Astrophysical Journal and the monthly notices of the Royal Astronomical Society, represent the deepest X-ray image ever obtained, collected over some 7 million seconds, or around 11.5 weeks of Chandra observation time. The images come from what's known as the Chandra Deep Field South. The central region of this image contains the highest concentration of supermassive black holes ever seen, equivalent to about 5,000 objects that would fit in an area the size of the full moon, and about 1 billion over the entire sky. The study's lead author, Neil Brandt from Penn State, says this one amazing image is allowing astronomers to explore the very earliest days of black holes in the universe and then see how they change and evolve over billions of years. About 70% of the objects in this new image are supermassive black holes, ranging in size from about 100,000 to 10 billion times the mass of our Sun. Gas falling towards these black holes becomes much hotter as it approaches the event horizon, producing bright X-ray emissions. It's usually very difficult to detect black holes in the early universe because they're so far away and are only producing radiation when they're actively pulling in matter. But by staring long enough with Chandra, astronomers were able to find and study large numbers of growing black holes, some of which appeared not long after the Big Bang 13.8 billion years ago. The new ultra-deep X-ray image allows scientists to explore ideas about how supermassive black holes grew in the first 1 to 2 billion years after the Big Bang. Using these data, the researchers were able to show that these black holes in the early universe were growing mostly in bursts rather than by a slow, steady, continuous accumulation of matter. The team also found hints that the seeds for supermassive black holes may be really heavy, with masses about 10,000 to 100,000 times that of the Sun, rather than less massive seeds with only about 100 solar masses. This therefore addresses an important mystery in astrophysics about how these objects can grow so quickly, already reaching masses of billions of times that of the Sun in the early universe. The authors also detected X-rays from massive galaxies at distances of up to 12.5 billion light-years from Earth. Most of the X-ray emission from the most distant galaxies likely comes from large collections of stellar mass black holes within those galaxies. As the name suggests, the stellar mass black holes are formed from the collapse of massive stars, typically with masses of a few to a few dozen times that of the Sun. To carry out the study, the authors combined the Chandra X-ray data with very deep Hubble Space Telescope data of the same patch of sky. They studied X-ray emissions from over 2,000 galaxies identified by Hubble that are located between 12 and 13 billion light-years away. A larger sample of distant galaxies will come from observations with the future James Webb Space Telescope, which will extend the study of X-ray emissions from black holes out to even greater distances. By detecting X-rays from such distant galaxies, astronomers are learning more about the formation and evolution of both stellar mass and supermassive black holes in the early universe. Further work using Chandra, as well as future X-ray observatories, will be needed to provide a definite solution to the mystery of how supermassive black holes can grow so large so quickly. I'm Stuart Gary. You're listening to Space Time. Okay, let's take a break from the show and talk about one of our sponsors. Audible's offering a free audiobook download with a 30-day trial to give you an opportunity to check out their service. Audible have over 180,000 different titles to choose from, such as Contact by Carl Sagan or A Brief History in Time by Stephen Hawking. Others include the unabridged version of The Hobbit by R.R. Tolkien, Divergent by Veronica Roth, and Born to Run by Bruce Springsteen. So many great books no matter what your taste. Over 180,000 titles to choose from. To download your free audiobook today, go to audibletrial.com/spacetime. That's audibletrial.com/spacetime for your free audiobook. Or you can click on the link at spacetimewithstuartgary.com. And now, back to our show. The European Space Agency's Gaia mission has identified a star which will come close enough to our solar system to affect the orbits of comets in the Oort cloud, that hypothetical sphere of comets and icy debris surrounding the solar system caught in the Sun's gravity well. A report in the journal Astronomy and Astrophysics claims the star, known as Gliese 710, will pass within 26 billion kilometres, that's 72 light days from Earth, in about 1.35 million years' time. To put that another way, it'll be just 13,365 times further away from the Sun than the Earth. And it's also important to note that the margin of error in these calculations means that the separation could be as little as 40 light days, and that means it may well be the strongest disrupting encounter in the solar system's history. Now, by comparison, the spectral Type M red dwarf star Proxima Centauri, which is currently the nearest star to the Sun, is located some 4.2 light years, or if you prefer, 1,553 light days away. Gliese 710 is an orange spectral type K dwarf star with about 60% of the Sun's mass and about 67% of its radius. It's currently located about 63.8 light years away in the constellation Serpens. During its close approach to our solar system, Gliese 710 will become one of the fastest and brightest objects in the sky as seen from Earth. Earlier studies of its proper motion, distance and radial velocity indicated that its closest approach would be less than a light year based on less precise Hipparchus data. The proper motion of Gliese 710 is currently very small for its distance, and that means it must be travelling nearly directly straight at us. As it passes the Oort cloud at some 51,500 kilometres per hour, that's some 50 times the speed of sound by the way, the star will gravitationally perturb comets and other objects in the cloud, flinging some towards the inner solar system. This so-called cometary shower could see up to 10 comets a year heading towards the inner solar system and the Earth for up to 4 million years. Dr. Fred Watson from the Australian Astronomical Observatory is speaking with Andrew Dunkley from our sister show Space Nuts about the implications of such a close flyby.
Gaia is a spacecraft that has now been in orbit for a couple of years. It is doing a marvellous job detecting the distances and motions of stars out to, well, much more than 1,000 light years, so well into the thickness of the galaxy. One of the interesting things that scientists are doing, though, with the Gaia data is looking at our nearest neighbours in space, the nearest stars to the Sun. And one of them, which has the rather less than romantic name of Gliese 710, it means it's the 710th object in Dr. Gliese's catalogue of red dwarf stars, in fact. But it turns out that in 1.35 million years, Gliese 710 will pass as close as 13,365 astronomical units from the Earth. What is an astronomical unit? Well, it is the distance from the Earth to the Sun. So astronomers think in terms of that as being a sort of baseline, if you like, a baseline measurement. In kilometres, that distance is 150 million kilometres. And so what we're saying is that Gliese 710 will pass rather more than 13,000 of those 150 million kilometres from Earth. Now, that might sound like a long way, and indeed it is a long way. It's actually, I think I worked it out as being 72 light days. If you think of the time light travel takes to get from that distance, it's a matter of days rather than hours. It sounds like a long way, and it is a long way, but it could still have an effect on the inner part of the solar system. And that is because we think that the cloud of comets that surrounds the Sun at a distance about twice the distance that Gliese 710 will pass within. That cloud of comets, basically, if it gets disturbed, it's called the Oort cloud. We know it's there because we see comets coming from there on a relatively regular basis. But if that cloud gets disturbed by the passage of another gravitating object, which a star is, then it could kick comets into the inner part of the solar system. And perhaps over the next couple of million years following that close encounter, we might find that the Oort cloud is stirred up and that the inner part of the solar system receives what you might call a greater flux of comets than we are used to. And that might mean that we have to watch out for things that might hit the Earth. It's one of those actually interesting links between the stellar universe, the universe of stars, and our own local environment. So it might actually produce, as I said, this bombardment almost of comets passing through the inner solar system. We think, by the way, Andrew, that has happened before because there are periods in the Earth's history when it looks as though there has been something stirring up the outer solar system, and maybe a passing star was responsible for that. They evolved very, very slowly. The Sun has evolved slowly over its 4.6 billion year lifetime, and so it will be largely unchanged in 1.35 million years from what it is now. And indeed, our Sun will be the same. What we'll see is a very bright object in the night sky, those of us who are still around in 1.35 million years, which will appear to pass really relatively quickly through the night skies as it passes by the Earth.
Wow, fascinating.
Although passes by the inner solar system, should I say.
We won't be around to see that, possibly, but humanity might not be either. That's a long way off, isn't it?
It is.
That's Dr. Fred Watson from the Australian Astronomical Observatory. He was speaking with Andrew Dunkley from our sister show, Space Nuts. Gliese 710 isn't the only star targeting our solar system. Backwards extrapolation of the motion of Gamma Mycropi shows that approximately 3.8 million years ago, it was only about 6 light years from the Sun. At that time, the yellow giant would have appeared brighter in the night sky than what the star Sirius is today. More recently, scientists have also concluded that Chaucer's star and its brown dwarf companion probably passed within 0.82 light years of the Sun about 70,000 years ago. Meanwhile, a 2014 report on the pre-press physics website archive.org claimed that there are at least 8 stars which will come closer to us than our current closest neighbour Proxima Centauri over the next million years or so. Among them is Barnard's star, a red dwarf now currently almost 6 light years away, which will come to within 4 light years of the Sun within the next 10,000 years. Meanwhile, the Alpha Centauri triple star system, which includes Proxima Centauri as well as Alpha Centauri A and B, will itself move a little closer to the Sun than it is now, with the 3 stars eventually getting to within about 3.2 light years over the next 30,000 years before swinging away again. Another one to watch out for is Ross 248, currently at a distance of 10.3 light years. It may become the closest star to the Sun in about 31,000 years' time, when it will be just 3 light years away. Mind you, that role will be taken over by Gliese 445 in about 40,000 years' time, when it too will be about 3 light years away compared to its current distance of 17.6 light years. It's also been estimated that the star HIP 85605 could pass as close as 0.13 to 0.65 light years from the Sun within the next 240,000 to 470,000 years. I'm Stuart Gary. This is Space Time. Astronomers have concluded that the supermassive black hole at the centre of our Milky Way galaxy is ejecting giant planet-sized balls of plasma every few thousand years. These plasma balls are the superheated remains of stars that have wandered too close to the monstrous black hole and were then ripped apart in gravitational tidal disruption events. Most, if not all, galaxies are thought to have supermassive black holes at their centres. The supermassive black hole at the centre of the Milky Way, called Sagittarius A star, is about 4.2 million times the mass of the Sun. When an object such as a star ventures too close to the black hole, it's ripped to pieces, simultaneously crushed, stretched and torn apart at the subatomic level. These stellar remains form an accretion disk around the black hole's event horizon, the point of no return beyond which material falls forever into the black hole's singularity. However, not all of the material can fall in at once, so some of it is flung back out again along powerful magnetic field lines, forming long streams of ionized gas. Now that would seem to be the end of the story, but it's not. New research shows that not only can this gas gather itself into planet-sized objects between roughly the size of Neptune and several Jupiter sizes, but it's then also flung throughout the galaxy. A single shredded star can end up forming hundreds of these planetary mass objects. What astronomers don't know is where these objects are likely to end up and just how close they're likely to come to Earth. A research team led by Eden Germer from Harvard University has now developed a computer model specifically designed to try and answer these questions. Germer's told the American Astronomical Society's conference in Texas that her calculations indicate these planetary objects could come within a few hundred light years of Earth. Once launched, one of these objects would only take about 1 million years to reach Earth's neighbourhood, 26,000 light years from the galactic centre. Although they must be glowing from the heat of their formation, they haven't been bright enough to be detected by surveys so far. However, future instruments like the Large Synoptic Survey Telescope and the James Webb Space Telescope may well be able to spot these far-flung oddities. The authors also found that the vast majority of these planet mass objects, some 95% in fact, will be travelling at speeds of over 10,000 kilometres per second. That's fast enough to be flung out of the galaxy completely. Since most galaxies have giant black holes in their centres, it's likely the same process is going on in them as well. Although these objects might be planet-sized, they'd be very different from a typical planet. That's because they're, quite literally made out of superheated plasma. And since different ones would develop from different parts of the original progenitor star, their compositions could also vary. The calculations also show they probably form much more rapidly than a normal planet. It only takes about a day for a black hole to shred an entire star, and it would only take about a year for the resulting fragments to pull themselves together to form a planetary-sized body. This is in contrast to the millions of years required to create a planet like Jupiter from scratch. The challenge will be to tell these objects apart from free-floating planets, which are created during the more mundane process of star and planetary formation. Germer estimates that only about 1 in every 1,000 free-floating planets are likely to be one of these second-generation oddballs. You're listening to Space Time. I'm Stuart Gary. China has carried out its first launch of the year, sending a Long March 3B rocket into space with a new experimental military telecommunications satellite. The TJS-2 satellite blasted into orbit from the Xichang Satellite Launch Center in Sichuan Province. Beijing used the heaviest version of its three-stage Long March 3B for the flight, equipped with 4 YF-25 strap-on boosters to aid the core stage's 4 YF-21C main engines. The strap-on boosters were jettisoned some 2.5 minutes into the flight, followed by the core stage after main engine cut-off or MECO some 20 seconds later. The second stage then ignited its single DAFY-20-1 rocket motor for a 3-minute burn, during which time the payload fairing was jettisoned, exposing the satellite to the vacuum of space. About 6 minutes after launch, the second stage was burnt out and jettisoned, and the third stage lit up its twin YF-75 engines for the first of 2 scheduled burns needed to place the satellite into geostationary transfer orbit. The top-secret TJS-2 telecommunications satellite is being used to test high-speed multi-frequency wideband data transfer for the Chinese military as part of an early warning defense system. The flight was followed 4 days later by the launch of China's new Kaohsiung 1A rocket from the Xichang Satellite Launch Center in Inner Mongolia. This first commercial flight for the new rocket carried 3 small satellites into orbit. The 3-stage solid-fueled rocket is designed to launch small payloads of up to 300 kilograms into low Earth orbit. The payload for this first mission included an Earth observation satellite and 2 small CubeSats. The Earth observation satellite will provide Beijing with high-resolution remote sensing down to a metre, reportedly to monitor forestry activity. The CubeSats include one designed to test narrowband communication technologies from orbit, while the other will monitor shipping traffic and provide China with navigation security. And that's the show for now. You can subscribe and download Spacetime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C.
This is Spacetime with Stuart Gary. For more, you can follow us on Facebook, Twitter, and Tumblr. Just search for Spacetime with Stuart Gary.
Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.